Welcome back to an exciting week in structural equation model, factor analysis and structural equation modeling. I don't want to forget both of those. But really, this class has been path analysis and factor analysis at this point. But you put the two together, and what do you get? Structural equation modeling. That'll be a test question. Just don't. There will be a test question that says, "What is structural equation modeling?" There you have it. But anyway, it'll be a multiple choice question because nobody has time to grade that. I'm just kidding. All right. Actually, I'm not kidding, but I will grade if I have to. Okay. First things first, let me start with an announcement on where we're going. Number one, next week, I'm not going to physically be around. I will be somewhere on the planet. Let's put it that way now. I'm going to a conference. Won't be here to give this class. So what I plan to do next week is to give you videos of Lisa's to watch from the last time she taught this class about item response theory. Here's my thinking. Today we're doing the example for CFA to teach you how to do CFA. You'll be able to do your homework. It's due next week, yada, yada, yada. If we get done with the example, then I will start the lecture for next time. And because I have her permission, I have her slides exactly as they appeared last time. So if you need to follow along for the example, including her font and her colors and everything else. So yes, if you need to follow along for the lecture last time, you don't have to trace down her slides. You can just go to our website, grab the slides. They are her slides, but they're under our link. You can find them and go from there. So once again, next week, no in-person class, no online class, just watch videos as your assignment for next week. We do have a reading assessment due and the homework due. Sound good?
Just
Yeah.
verify, is this lecture 4A, 4B, and lecture 4?
Lecture 4A and 4B, if 5's on there, I have a typo, so I'll fix it.
Okay.
Yeah. Her version.
That must just be.
Yeah, I'm sorry. Yeah, there's her version was lecture 5 and mine's 4. So
All 6 of them.
all the videos, I tried to make it stopped at the timestamps that were relevant to the slides, so you just have to click the link and it should pop at the right time. So tried to make it as easy as possible for you. I'm sorry to have a conference to go to. Not that sorry, I guess, but well, we'll see. It's in South Bend, Indiana, so that'll be, got an interesting travel schedule ahead of that, though. Yeah. So today is a day where I got to roll up the sleeves. All right. This is how it works. Right. We're going to get into an example, but as I'm rolling this up, do you have any questions for me about what you may have learned last time? Anything unclear? Any jokes you'd like to repeat that were so funny? Okay, maybe not the last one. Nothing. Silence. Crickets. I like it. Okay. You don't have to have questions. That's fine. Shall we begin with the example?
Yes.
Okay. So at this point, you've seen factor analysis and factor analysis. You've seen the underpinnings. You've seen sort of the theoretical basis for it. You've seen the mathematical model. Once again, if we would have observed the factor, it's a series of simultaneous regressions, right? That's the story of this class, right? Doing everything simultaneously. So to walk you through the process of, so you can understand all that on the concept just fine. But I think what this example is going to do is teach you a little bit more of the art of using these models. I hate to say that term, although I do find these very artistic. Does anybody else see beauty in factor analytic models? Thank you. Just look at this. If you don't, that's okay too. Art is in the eye of the beholder, right? But why I say the art of this is because the science of it is the math, is the technical side, is we can talk about all the math behind it. But in practice, that's all great until you collect your data, and that's where things start to fall apart, right? I keep saying it, but what's that saying? Everybody has a plan until they get hit in the mouth. Every theory has a hypothesis until it meets data, right? You've got to do something else with it. So the example today is I'm taking the simulated data set. Online, you'll see a real version of this. Actually, you know what I'll do? I kind of want to do the real version, don't you think? Don't you deserve real data? The messiness of real data. I cannot give you the real data, but I can give you the results for the real data. The simulated data is there for you if you want to go and grab the file and download it. All right, let's do that. Real data. Here we go. So this is an example data using the forgiveness of situations scale. There were 1,103 people sampled, and there are 6 items. Each item had a 7-point Likert scale. And the items were coded with 1 through 7. Here, the questions are, when things go wrong for reasons that can't be controlled, I get stuck in negative thoughts about it. That is supposed to be, the R afterwards indicates a reverse coded item. And in this example, we will convert that number. So what this turns out to be is 8 minus the number they chose. Right? So if they chose a 7, it's a 1, vice versa. Later in class, we'll show a method factor for it as we go further. So when things go wrong for reasons that can't be controlled, I get stuck in negative thoughts about it. So that is the opposite of forgiveness, and that's why that's reversed. Although we all have a definition of forgiveness, but evidently that's part of it. Maybe we all don't. I don't know if I have a definition of forgiveness. I don't think I've thought a whole lot about it apart from I probably should practice it. Yes?
Do you have to reverse code it, or do you just
No.
have to keep in mind what your variable stands for to interpret correctly?
Keep in mind what it stands for to interpret correctly. There's nothing mathematically sound about reverse coding it, but what will happen if you don't reverse code it is that the most likely it will have a negative relationship with the factor, which means a negative factor loading. There are a few cases, not in this class, in Bayesian psychometrics that might cause a problem. Where that might cause a problem is in some algorithms, Stan in particular, and I'm looking over here because both the TAs know this class. What happens in Stan when you estimate an IRT model where the factor loadings or the discriminations can go in either direction? Do you remember? Stan almost always converges to a multimodal solution, meaning some are all of them are positive or all of them are negative, right? It's almost like reflected about 0. And where a reverse coded item could throw fits would be in that situation. Again, narrow, but not necessarily, so long as you interpret it correctly, it's not a problem. Convention, now, on the other hand, is a bigger problem. So if you submit a journal article to, I'm associate editor for the European Journal of Psychological Assessment. I know that sounds crazy. What is that? It's people publishing reports about surveys like this. I think conventionally, when you, as associate editor, many of you who've heard about this before, it's really hard to find reviewers, but when I find them, they might be like, oh, you didn't reverse code. So there may be, by convention, it's convention to do that, but it's not always the case that we have to. Okay? Yeah. I'm sorry I give way too long answers, but I just feel like I need the breadth of information. Okay. With time, I can be understanding of bad circumstances in my life. That sounds like forgiveness. Actually, hang on one second here. I want a dictionary. There it is. Ha! Well, this is my computer. That is what I get. So do not cross me. There's no forgiveness on this machine. This is an unforgiving Mac OS. So what I'm trying to do here, and what I should have done in the example, is try to provide, when you're trying to measure something, what forgiveness is. It's a psychological trait, but it's definitional, right? And without that definition, we may all differ slightly in what it means to be forgiveness. What that translates to from a validity sense is we would each say that different items shouldn't belong, or maybe shouldn't belong exactly, or maybe there should be some other caveat, some other factor that goes with them. So let's define it first. Here we go. Wikipedia, thank you. Forgiveness in a psychological sense is the intentional and voluntary process by which one who may have felt initially wronged, victimized, harmed, or hurt goes through a process of changing feelings and attitude regarding a given offender for their actions and overcomes the impact of the offense, flaw, or mistake, including negative emotions such as resentment or a desire for vengeance. Okay. Does that make sense? That seem fair?
Yeah.
Anybody want to have a different opinion of forgiveness? It's okay. You can do that. All right.
Summarize it in 10 words.
Forgiveness means letting go when you feel wronged. How's that? Better? Or changing your feelings when you feel wronged. Maybe that's it. Anyway, and I almost spilled my drink, but thankfully lid technology is on point. It is. I mean, I can't open it now unless in the front you want. Actually, you've got a coffee and you've got 2 drinks, so I better not. Okay. Going back to, nope, that's not it. Going back to the example. See, I brought this handy dandy mouse, but now I'm like, what am I using it for? All right. So let's go to item 3. If I am disappointed by uncontrollable circumstances of my life, I continue to think negatively about them. So is that forgiveness? What do you think? It's reverse code. So opposite of forgiveness. But is it close enough, even if you reverse it? Does it seem in the ballpark? See, I'm almost like, hey, continue to think negatively about them. Is that rumination? Is that some other process? But I don't know.
I would say you haven't necessarily let that go, like up or down.
Yeah. Now, I know some of you are trained in things that counseling. And so I would defer to your opinion on this, or anybody who may.
Opposite of having to say you don't think about it anymore. You continue, it just gets
True. I'm doing this exercise slowly because this is the part that matters. This is the part that I always in school was like, yeah, get to the statistics. Words, thoughts, feelings, I don't care. Get to the statistics. But as I gotten older, it's like, well, this is the part that actually does matter, right? You have to make, when you're using the C in confirmatory factor analysis, confirmatory, it takes thought and effort to build your scale. You should be doing that even if you're not using the C, and most people do, but this is part of the thought and effort. I eventually make peace with bad situations in my life. That sounds like, I think that's good. It's really hard for me to accept negative situations that aren't anybody's fault. Yeah, I'm good with that. And then eventually I let go of negative thoughts about bad circumstances that are beyond anyone's control. Again, I'm not sure that's forgiveness, but maybe it is. Maybe it is. Maybe it's anti-rumination. Is forgiveness anti-rumination? Is that it? Yeah, okay, yeah. So, plausibly forgiveness, we'll call it that way. So again, the response anchors are 1 through 7. And here's one thing that I will tell you that Lisa drills in her classes, and you probably hear about it next week, but also in every class. When you give out a survey, label what these mean. Right? If you label sort of the midpoint or somewhere in between, you're leaving that up to the impression of the person giving you the answer, and not everybody will use the same standard for each item. So if you're doing survey research, don't assume that when you see a 1 through 7, people know what each of the anchor titles mean. Write them down. Yeah.
You can also try not to make it a bi-directional like this. Try to make it unidirectional makes it easier to
That's right. The other thing that's interesting here is that this is asking someone to recall kind of a rate, right? Is this more often false? Is this more often true, right? That's a tough, like psychologically, a rate is a tough thing to do. How many nights of the week last week did you get interrupted sleep for 20 minutes or more? Let me just go with that. Anybody know the answer to that? More nights than fewer? All right. What's that? Half of them? Would you say, okay, I was going to say, but no, but just like, but imagine it. Yeah, if you have that, that's what I'm saying. You have the data. Okay, let's try this exercise. Think to yourself in the last week, if you have a sleep tracker, you can do this right now. How many nights a week you had interrupted sleep of 20 minutes or more? 7. Now,
I don't mean to strain
you know that, yeah. I'm going to go with 2. 5, maybe? All right, I'm going to look at mine. I'm not going to show you mine, but I'll look at mine. And I'll tell you. I'll tell you about mine. Do I dare? These live examples, I got to cut them out. All right, where's sleep? What did I say my number was? I said 2?
Yes.
Okay, let's see here.
That was the hypothesis.
All right, I had 22 minutes interrupted in that last night. And then on the week,
Total or like it has to be like continuous.
total, I would say total.
Oh, well then yeah, so terrible.
I can't break it down by day as well, but it looks like it was probably closer to 4 for me. So point I'm trying to make is this is stuff that, like, I don't know about you, sleep disturbances are pretty tough, right? You can feel it. You definitely know when you feel sleep deprived. You said I look tired as I walked in today. I'm all right. I'm not tired. I'm just grumpy. But that's just, I hear it's National Grouch Day, celebrating my people. Not to you all, though. You make me happy. Makes me happy. But an easily identifiable, intimately familiar feeling is difficult to judge a rate. Now, tell me about hypotheticals about letting go. How hard is that for someone to reply? Right? That point I'm trying to make is that's really difficult. And this is part of the issue that some people would say, like, I love quantitative methods, but getting these type of data it's going to be a lot of error to them. There's going to be a lot of noise. And that's the hard part about it. So I'm setting this up to be, it's difficult to measure things, particularly when you're asking people to use self-report, self-recall, even if the person is the wellest of intentioned at trying to remember things. That might not work. Yeah.
Is it better to have a shorter scale or something like this? If you could not come up with names for all 7 of these, should they have just not just collapsed into 4, for example?
That's a great question. I don't know the answer to that. There is a field of inquiry, survey research methodology. What is the answer?
The answer is if you can't label every point, you should shorten it, but it should still be an uneven to keep that midpoint. Yes.
Yep.
Unless you want to force a choice.
True.
Almost always it's a bad idea to force somebody to make a choice.
True. Yeah. So forced choice is tough. Exactly. Right. Because what if it doesn't apply? And a person then has to go and map their feelings onto something that doesn't apply. I agree. Now,
Theoretically,
that would be nice. Yeah, over the last month. Yeah, so the more detail that you can build into the survey instrument, and I'm dwelling on this. I know this is not the math part of what we're doing. It's survey research, but it's so important. Actually, this is Katie Broughton's Broughton. Sorry, Brian on. I'm going to put a plug in for it. It's a great class. I've heard great things about it, and survey research is incredibly important. So those of you who haven't taken it yet, consider trying to get on the waiting list. It's a very popular class.
It's very small.
It's very small. Yeah. Uh, survey research and design numbers. It's EPLS 6209. Yeah, it's a great class for trying to understand the process of the structure of this. Right. So that class is teaching you about how you should structure this.
Yes.
There are, I assume, personality or counseling or other classes that teach you about the structure of what forgiveness really means mentally. What the heck am I good for? Let's talk about the structure of how we analyze the data. Shall we do that? Okay. Yes, question. Aaron?
For the Likert scale,
Mm-hmm.
0.2, 4, and 6, I was wondering what that.
That's a great question. So this example came to Lisa Hoffman by way of a different collaborator, and they did not label those points. So we are left to try to infer what that means. If you were a subject or a participant in this study, what would you think that would be? Yeah, I would say, okay, so 1 is almost always false, and 3 is more often false. Is that would be maybe equally false and true? You see the problem with it, right? Yeah. Right. Here, you want to blow some heads up? So the methodology for this is no different than the methodology we use for scoring the GRE or the other measurement tests. And we're talking about needing to say to a person, let's not push them to force a choice, but on an achievement or ability tests, cognitive tests, sometimes we call them, you don't have that luxury. Should you? Should that be another option? Should we just cancel, make a value 0? That we have to worry about gaming a test. This scale, forgiveness, I don't think people are trying to fake. But if you're in a personality context, there's a whole bunch of research on people trying to understand what's expected of them. Like if you get hired at an employer, how many of you have been applied for a job and had to fill out like a survey, like a personality survey? I've done that before, right? Do you try to figure out what the employer wants to see and then fake it? right? Because there's a whole line of methodological research that tries to detect that as well too. Myers-Briggs, yeah, yep, yeah. There's also MMPI, or parts of the MMPI. Those are two alternative for forced choice questions, or at least used to be. Okay, so we bring in our data to R. Here are the 6 items. We'll note the R on the 3 of them. The odd items are reverse coded. This is the correlation matrix that you see here. Well, what are we looking for when we want to see the correlation matrix? What's that? They want to mirror each other. Well, let's think of it this way. There's not a whole. It's really hard to decipher, right? So what do we know about a factor? If there's one factor that underlies this survey, we haven't even talked about what the structure is, right? If there's one factor, we would expect roughly a uniform set of correlations, roughly. If there's more than one factor, you would expect sort of clusters of higher correlations of items within cluster, lower correlations of items between, something along those lines. It's just hard to derive that information. I will tell you, when I look at a correlation matrix, the first question I have is, what's the lowest correlation? And what's the highest, right? So 0.255 here is a low correlation. That's fairly, actually 2.240 is even smaller. How about that? Yeah. That's a great question. So the question is, if the correlations are super high, at what point do I worry about dropping it out? I don't know the answer to that. I don't have a quantitative, like a great measure. It's a matter of degree. Yeah, that would be a reasoned approach would take the items into consideration, certainly. But a mathematical, so what we're in between here is the philosophical, right, which is the design, right, Tevin, and then the mathematical, which is if those two items are as that correlation gets to 1, the scale itself really is just those 2 items, right? And so, like from a mathematical perspective, now you're talking about, ooh, is that good? I don't know where the right answer is for that. That is something that I would encourage trial and error. So that's, all right. Yeah, there we go. Sample means, I'm looking at these. When I look at these in the factor analysis sense, there's a couple things I need to think about, right? With the 7-point Likert scale, remember our factor analysis model is assuming the data are normal. It's not conditionally normal like a normal linear model would be because we didn't observe F. So if we assume F, the factor itself, is normally distributed, and we assume each item's error term is normally distributed, they combine to give us a normal distribution. And a normal distribution has several features that the mean can tell us a little bit about. Number one, we need a normal distribution to be symmetric, not skewed, right? What we would be looking for in the mean here are the means somewhere near the middle of the scale. That is a factor, a very rough factor analysis assumption idea. Yeah. No. You could. This is not a 1-to-1. Yes, you could have it so that it is 0. Like if people picked only 3 categories and they picked the middle one, now that's a symmetric idea. It's possible. It also suggests that perhaps you don't have enough anchor points or you have enough. Anyway, the variances. What are we looking for here? We're looking for variability. Period. Because if we don't have variability, if everybody's answering one way, we will not be able to include that item either. Right? So here, the fact that these are non-zero is good. Okay. So to do typical, this is translating correlation into covariance. Technically, to do a CFA analysis, you really only need the means, variances, and either the correlations or covariances, but we like to use the raw data. Right? So let's look at the raw data themselves. And here we go. So what are we looking at here? We have a lot of people who are, these are negatively skewed items. Are they symmetric? Not so much. So this is a situation where most people will still do the factor analysis, but from a mathematical point of view, and again, that's my contribution to this, it's not advisable. Right? We should really be treating each of these as separate categories. Well, turns out that's next week's class. That's the stuff online. Right? That's what factor analysis or item factor analysis, item response theory, sometimes called item factor analysis, seeks to do. Okay? It will treat each of these categories as discrete choices a person can make, whereas in the CFA model, we're just assuming that there aren't categories at all. It's continuous, fully continuous. Right? So a score of 4.237 could be possible. It won't be possible, but it is. That's what we're assuming. How are we doing so far? Okay. Should we get to our first model? You'll note. Yeah.
About the variance that you change the sample variance to like the maybe that population variance that multiply.
Oh, yeah. Here,
Is that your rationale?
I'm only trying to make numbers match up. So what ends up happening is, if you're using maximum likelihood for estimation in Lavon, M+, or elsewhere, the estimates of variance of items are the maximum likelihood version, which is variance divided by n. But if we use the variance function in R, which is that function right there, it's actually n minus 1. So I multiplied and I basically rerouted this to make it look like the by n version. It's a small difference, but it will cause a little bit of rounding errors. That's a great question. Thank you for observing that. Any other questions?
Would you want to test to see if those are relatively equal?
No, they don't have to be equal. That's the thing. No, they don't have to be equal. We can handle it. There is our residual variance so basically, if you think of this variance, why am I saying it doesn't have to be equal? Let me unpack that for a bit here. This variance, when we put the model onto it, is going to be in part due to the factor, right? Basically, if we use a standardized factor, the contribution for the factor for an item is its loading squared, right? And part due to the unique variance. Well, the rest of it being the unique variance, right? And because there's two different parameters there, we can have widely different variances, right? So that's okay. Good question. Widely different variances would be the situation you talk about. If you had a quote-unquote symmetric item where people were only picking 3 categories, that would be a smaller variance than a symmetric item that would people pick 7, right? The other thing I will note about Likert items is that the variance is constant. The maximum variance is fixed. Because they're categorical items, there is an upper bound to how much variation there can be. That, again, is counter to what the normal distribution says as well. So just another thing to think about as you're trying to take a factor analysis and put this onto items. Okay. So now comes the hard part. Before we can get to Lavon syntax, I didn't even talk about a model. So what are we thinking here? Is there one factor of forgiveness? One dimension of forgiveness that these items measure? Is there more than one? I would think there's more than one, right? I'm reading these, I feel like we've got rumination going on, we've got letting go going on. But, yeah. But if you were like me, when I was in grad school, I would be handed these data and told, hey, go fit a factor analysis. So where would you start? Let's start with 1 and see how well it works. Right? Look at that. It didn't blow up. Front row is safe. Okay, so let's start by doing 1. So the model here, this is where I'll switch over to R, where it looks a little more natural in R. But a model in Lavon does the same, looks very similar to a model in the path model in Lavon, right? In that, and forgive all my commenting here, when you want to define a factor, we're going to define the SIT factor, the forgiveness, it's basically situational forgiveness. What you use is an equal tilde command, right? So remember, in path analysis, the tilde was reserved for intercepts or predictors, like what's being predicted. In factor analysis, this says I'm defining a latent variable by and then all these items. Remember, in syntax, then what happens is your definition of the factor shows up on the left. That's SIT. That's your name. You can name it anything you want. Not anything you want. There are some restraints in Lavon and R, but basically you have control over that. On the right-hand side of the equal tilde go your items. Those are the names of the variables in R. Yes? Yeah, this is only one factor. So when we have more than one factor, we'll have another line, we'll have a different name for the factor, and then a different set of items that load onto it. So the other thing I want to note here is this looks like the sum of each of your items equals the factor. But don't be fooled. It's not. This is shorthand to keep you from having to write 6 different lines of code, I think. Okay? So, once again, in Lavon, single tilde is reserved for, this is a regression of some sort or an intercept. Double tilde represents variances, covariances, or their residual counterparts. And now equal tilde is a factor, a latent variable. There was another one that was colon tilde, which was a defined term that we used in indirect effects when we wanted to multiply parameters together to come up with an indirect effect. Yes?
We haven't identified which number of factors based on statistics will be most appropriate.
But we don't. So we go into it thinking, we don't. There's nothing methodologically that will allow us to know that with good certainty. So what we are doing is we're saying, no, we don't have statistics to determine this. We're going to assume that the person who wrote these items thought there was one factor. And we're going to confirm or disconfirm whether that's true. Yes?
Is it an equal colon for indirect?
Is it? Maybe it's equal colon. I don't remember. Colon shows up there, and I don't remember which one it is. Yep, there's an equal somewhere in there. So what we're saying is there are 5 items right there. Now, I mentioned this the last couple times. Depending on which function you use to run the model, there is a CFA function. CFA stands for confirmatory factor analysis. If you want to use it shorthand, all you need is this line of code right there. The CFA function will then add to each item the item intercepts, any also unique variances as well. Okay. However, here we're going to use the Lavon or SCM command. Let me just double check. Yeah, the Lavon command. The Lavon command says, I'm not assuming anything. If you want a parameter to be in your model, you got to specify it. Right? It is explicit to everything that needs to be there. You have to specify it. So in the Lavon command, I'm doing this to show you where all the parameters show up. So I'm giving you extra here, but when I run this on my own, I probably will only do that to begin with. Okay, what does that mean? That means here, each item gets an intercept, right? Remember, for each item, the linear model is like sit1r is equal to intercept plus loading times factor plus residual, right? So, what's that? Yeah, that's right. Circle plus square equals triangle there. Here we've got 6. I'm sorry about, maybe I misunderstood what you were saying. Anyway, we got 6 items here. Each one of them gets an intercept. The residual or unique variances show up on the next line. That's each item double tilde itself. You'll note that none of these indicates a residual covariance. Remember, we could add one, but that weakens our validity argument as to whether or not there's one factor underlying the scale. I set the factor variance just for fun to be 100. Why did I do that? Oh, just to show that I could. Doing there. Let me make sure this wasn't a didactic thing. Nope. That's only in my silly syntax. I'm sorry about that. Let's get that out of the way. What I was doing that for, I think I had a question way back in the day and I added it to my stack of files, which was what happens if we rescale it? Can we do it? Yes, sometimes, but not always. Why I say that is, in theory, yes. In practice, computationally, depending on where the starting values are and where you put your factor variance estimate, you may have numerical instability that causes the algorithm to stop. Yes,
Do you think that maybe you have 1 star as opposed to 100 stars? So you get like, oh, the chance
I could do that. Yeah, I could.
latent variable.
Yeah, well, it turns out there's a definition of the latent variable later as an option we have to add. Yeah. So we could specify it here, but we are going to add it here with standardized latent variable. Actually, nope. Because I have standardized as false, I do need a 1 star there. There we go. So what am I saying here? So we are specifying the factor variance. We're setting its value to 1. But again, there is a command in Lavaan where we wouldn't have to do that. It would do it for us. This is me being extra detailed because there may be a part of your life where you have to do something with one or more of these parameters and giving you the code to do that.
If you had that true, which would force above 1, but you put something other than 1, would it override my input?
I don't know. Probably. We can find out though.
That'd be
Yeah, let's see if we find out. Let me just need to double check that my code is right now. Oh, here we go. Yeah, I did put a 100 in there. And if I look at my results, there is a 100. So let's rerun this. It's the subtle things, man. Every line I got to go and look at, and I don't have the attention span to do it evidently. Oh, well. Okay, there we go. Okay, so now that we have everything together, we will use the Lavaan function again. This is the same function I've been using in path analysis. We specify its model. We tell it its data set. The estimator should be MLR, although it expands to the other line here, so MLR. I'm going to mimic M+, just in case you're using M+, and I'm not going to specify the standardized factor. That's because I specified it in my syntax. Okay. Questions on my syntax?
Going back to the factor variance,
Mm-hmm.
is it 1 or is it 100?
It should be 1.
Okay, just making sure.
Yep. The 100 there was in response to a question that I remember,
Okay.
and I did it live, and then I saved the file, and I didn't see that line when I recreated this example. My bad.
I have it right.
Question?
Yes, sir. Can you like estimates lines you share with us? I think it says ST dot equals false. So what I guess is true
Yes. So this option I turned to false so that I could fix it myself in the code. That's where I had the 1, and that's actually why I was able to do 100 and not have a problem either. If you specify true, if you turn it on to true, you don't need to specify the factor mean or factor variance. It'll be fixed. The factor mean fixed to 0, factor variance set to 1. Sorry for the confusion. Other questions on the syntax? So brief summary. Factor analysis in Lavaan equal tilde. Factors on the left, real data are on the right, separated by plus symbols. Okay? All right, let's take a look. Did it fit? So remember, we have to go and check the model fit like we did in the last time in path analysis. This model test user model, anybody want to take a stab as to what that represents one more time? This is refresher. This will be on your exam.
It's the one thing that I know I'm going to have on my note sheet.
Yes, it will. Yes, you will.
It's hard for me to recall.
What if I said,
just like the same number of degrees of freedom.
well, not quite. I won't say that. With degrees of freedom, we know this is over-identified because it's bigger than 0. All right. The scaled term, we should be looking at that as our corrected MLR statistic. The question is, what is this chi-square test statistic being a test of? And I think we might have had an answer.
It's against
The saturated model. That's right.
and it's testing
does our model fit as well as the saturated model? Because you have to remember, in the saturated model it subsumes all CFA models, right? That means when you estimate a multivariate, basically the parameters of a multivariate normal distribution, and that can be estimated are all possible CFA models fall underneath that. They're special cases, or they're subsumed into it, right? We call that the process of something being part of a bigger set, right? So what we want to know is does our model fit the data as well as the saturated model? The other thing I will add to that is the saturated. So if you assume the data are multivariate normal, big if you assume that, then no other model can fit better than the saturated model, right? Now, in practice, if the data aren't multivariate normal, then your multivariate normal saturated model may not be the best fitting model, but let's leave that aside for right now, okay? Let's assume that's the case. So this is a test of our factor model versus the saturated model. The p-value is, we can't even see what the decimal place is, it's 0. We would reject the hypothesis. So what are we determining here? Does this say that we fit or we do not fit? Do not fit, right? The null hypothesis here is that our model fits as well as the saturated model. The alternative is our model does not fit as well as, or the saturated model fits better than ours. And because we reject that null hypothesis, we must say that our model does not fit the saturated model. Yes? Yes, this is your likelihood ratio test of model fit, right? This is the most powerful test, and this is the one that almost always will tell you your model does not fit. Okay? So in a practical sense, if you only had this, you'd never have a fitting model. And then if you go with my inaccurate but brutal summary of the model fit world, it was, okay, this is an absolute sense we fit or we don't. The other indices are versions of how close we are to fit. Right? The cynic in me says, well, the other indices allows us to publish even if we don't achieve fit with this. But the practical person in me says, this is yes or no, whereas the other indices are like a degree of how far. Does that work? Okay. So according to the saturated model, model does not fit. What is model test baseline model? That is, again, another likelihood ratio test. And to narrow the question I'm going to ask you is just tell me which two models are being compared. We'll worry about null and alternative in just a moment. What's that? Saturated model is one of them. What is the other model it's comparing?
Is that the independent variable?
Yes, independent variables model. So this is comparing, basically, model test baseline model is asking the question, do you have any non-zero covariance in your data? And why that's important is if you have a bunch of zeros for all the covariances, you don't have a factor. The end, right? So if this, let's go with one more thing. What is the null model and what is the alternative? So once again, two models here. We have saturated and we have independent variables, right? Independent variables each variable has its mean, each variable has its variance. Each covariance between all pairs is equal to 0, right? So saturated versus independent, which is the null model and which is the alternative model? I see the looks on your face. So let me give an example here. Well, this is good. Let's talk. Okay, so give me your rationale. No, this is good. You said null was independent. Mm-hmm. Well, you were right about what was the null model, but the rationale was not there. So let me give the definition. A model is nested. One model is nested within the other. When what are the symptoms of it? Number one, you can by adding parameters to the null model, you achieve the saturated model. Basically, think of it that way. Okay. So in this case, the null model is independent, and that's because the covariance matrix has zeros in the off-diagonal elements. The saturated model is the alternative model, and that's because if we were to add that covariance parameter to each of the zeros, we would achieve the alternative model. Another symptom of that is which has more parameters, because the null model has to have fewer. It cannot have equal, it cannot have more than, because otherwise it's not subsumed into the parameter space of the alternative model. You can't, yeah, it's almost, it will, yeah, in a multivariate,
Is the saturated model always going to have the most?
always, yes. And your model will have less than or equal to because it's subsumed into it, but your model will never have more unless you're outside of the CFA framework altogether, where you're not in multivariate normal land. So yeah, this is a feature of like when it comes to likelihood ratio tests, you always have to pay attention to which is null and which is alternative because that sets what the test means, right? What you're rejecting by it. Yes.
The no on the left column for the radio proportion.
Oh, the left column right here? No, these are both this. So the two columns here are the maximum likelihood estimate and the maximum likelihood rescaled or robust maximum likelihood estimate. So we will always look at the right-hand side of these two columns. But the test is the same. The numbers are different because what ends up happening is when we fit the data, we calculate the scaling correction factor and it adjusts the likelihood based on how kurtotic the data happen to be, how peaked or flat the tails are. How are we doing? Is this good? I like the questions. I like the discussion. I feel like we're getting some practical knowledge here, right? Maybe I'm wrong, but I'm going to look on optimism. I'm going to have forgiveness too, because that's all this is about. But all right. So what does this tell us? What's the p-value is 0, so we reject the null hypothesis. So it tells us at least one of those 15 covariances. I know there's 15 because that's the difference in those are the only parameters different. At least one is not equal to 0. But we saw that ahead of time when we looked at the correlations. A correlation is not a covariance, but it's a cousin of a covariance. It's a rescaled covariance. But when the correlation is 0, the covariance is 0. And that's why. Got one more minute. Let's talk about CFI and TLI. So here, I like to look at the robust versions down here. This is a model fit index. We want this to be above 0.95. Both of those are too small. So by CFI and TLI now, we have more pieces of evidence that the model does not fit. Right? We can go one step further in the seconds I have remaining. RMSEA, I will look at the robust column. RMSEA, we'd like to be less than 0.05 ideally. 0.08 people talk about, and those are old standards, but that's largely what we get. We have a 0.195. The p-value is very obvious here. Absolutely, it does not fit. That's what that says. Does it have excellent fit? Heck no. Does it have likely really bad fit? Yeah, 100%. So on that note, how about we pause for 10 minutes? I'm right on time. I got my second hand on today. Right on time for the break. Come back in 10 minutes and we will talk more about what to do next. But we're back. Okay, we had a question in between the break asking specifically, can an interaction predict a latent variable? Or is that what you said?
Yeah, if you have an interaction term, plus interaction term.
Well, let's talk about what we mean there. So for an interaction to be present, you have to have a combination, right? So let's imagine we have y1 and y2, okay? Let's just take a one factor model approach to this. P1, P. Okay, so what do we have here? We have two single factor models. What do we have that could interact? In a one factor model, when you say interaction, when I hear interaction, I think an interaction needs to be like right here, right? So what has to happen if you were to do that? Well, first of all, you'd need 2 dimensions, 2 latent variables underlying the factors, and this might be 2 different ones. Now, we have to have enough items on each, measuring each to make it identical. So then what we could effectively do, this would be lambda 1, 1, 2, 1. We could then, let's say for item 1, maybe item 1 also measures factor 2, right there. Now, it is possible in that case, you could have what's called a latent variable interaction. We call this lambda 1, comma, and I'll do 1, 2 here. Notating it is really tough. FP1, FP2. So what does a latent variable interaction represent? It represents a multiplicative product of the factors times a regression coefficient adding to the line. So that is possible. Not in Lavon and very limitedly in M+. But let me talk a little bit about that. This concept right here is called a latent variable interaction. Latent variable interactions in the CFA world are very limited. So that people have done research on it, good research on it, very limited. And honestly, like, I would call it like, if you think of the distinction between basic and applied research, basic being sort of foundational, applied being sort of empirical. Some of the basic work has been done, but it's the basic of the basic. There is another field in psychometrics that started there, and that was actually the field I was in. And that was in diagnostic models, sometimes called cognitive diagnosis. Those models actually started with items that looked like this, where there was an intercept, no manifestation interaction. That was not good either. Right? What's that?
Because there'd be multiple dimensions.
Yeah, there'd be multiple dimensions. This is a model called the DINA model. Actually, Agyung would like to give you a lecture about these models. She's not here right now. But in November, because she wants teaching experience, I've given her the chance. She will be giving you a lecture for an hour and a half about this. But I wanted you to ask this in class because it is a way that I can introduce not only this concept, but also tie in a preview of when she'll be giving her first lecture. She's very nervous about it, so be nice. Sorry, Agyung, if you're listening to this. Maybe you're not nervous about this. Actually, I don't know if she's nervous about this. She's stoic, always. She's great. Now I feel like I put my foot in my mouth. I'm not nervous about her willingness to present. I have the utmost confidence in her. She's excellent at what she does. So let me put it that way. How's that sound? So does that answer your question?
Yes.
When you said interaction predicting,
I
is
was
that...
thinking of something of that nature.
So I think you had said, can we have an interaction predictive factor, which would be something like this, FP1 is equal to, and now what is that? And the answer is yes. Like let's imagine we want to predict the factor with a set of other variables we've observed that aren't measured. Maybe we're going to talk about predicting it with demographic characteristics, race, ethnicity, gender, et cetera, right? Then yeah, that could absolutely happen. That's just things we've observed. Absolutely can do that. Okay. Things we haven't observed is a lot harder. And the reason for it, one last bit of trivia, is that when you put this factor interaction in, y can't be normal anymore. If y can't be normal anymore, our likelihood function for it falls apart. That's right. We need to condition it or otherwise remove it. And that causes all sorts of estimation errors. Y can't be normal. If you look at y2 here, where I didn't put the interaction again, f is normal, e is normal. The sum of normals gives you normal, and then the question is, are they shifted? What's their variances, et cetera, right? When you have a product of normals, it cannot be normals. If they're a product of standard normals, that actually is a chi-square with 1 degree of freedom. Again, more statistics trivia. I did love my stat training, but the latent variable interaction makes it incredibly difficult to estimate. You cannot just you can't write the likelihood function without f in it. And that means now we have to do some numeric integration to get f out of the likelihood. So this is why you don't see it in a lot of places. Okay? I think latent variable interactions are cool, and if I can add one other point to it. This is a bigger topic, and that's why I know we're sort of disjointed from the math part of it and the theory part of it. This goes back to the theory part. There is a belief in psychometrics. Again, I call it psychometric dogma, which is these are beliefs that are passed down from generation to generation that probably don't stand to be there anymore, right? One was a good item is one that only measures one thing, right? And this came from the factor analysis idea, right? When you've got exploratory factor analysis, when you've got all the loadings, allegedly, and you want to see one item load onto one thing and that's it. Why is that the case? Well, in exploratory factor analysis, it simplifies your job of explanation. But I would argue, and it sounds like I'm in a very small club, so don't get me wrong, there are people who, the old guard really hates it when I say this. There are people here who absolutely disagree with me, and I'd love to have that debate, but they don't want to debate, so that's not going to happen. But what I will say is, what's that?
They don't go slow.
Just like debating, and that's the problem. Nobody likes to debate me.
I'm going to tell your son that, and he'll probably like,
Oh, he's a debater too. Oh my, this guy, he's got lawyer written all over him. Like if you set down this is the rule, he will find a loophole. And then he will argue that he was fine because I didn't include that as part of the condition. Right? You know, so, and then see, and me as dad, I encourage it because at least he's thinking. Anyway, that being said, why would you, when you I think it matters as to what you're measuring. If we're measuring forgiveness as this broad, very gross level concept, it's hard to envision why you'd have multiple dimensions on an item. First of all, we haven't even defined multiple dimensions in this example. But when we start measuring more nuanced or fine-grained ideas, in the case the work that the diagnostic models have started in was educational measurement of very small skills in mathematics, right? So if you've got, if you're teaching algebra and you're teaching a lesson on functions, right? There are a whole bunch of...
There's a myriad of things that go into that.
Here, let's do this. We'll look at...
I used to have a whole set of books like that from like...
So in Iowa, we have a set of standards for mathematics. These are educational standards that teachers teach. Each district gets to set what they call their scope and sequence, and if this K-12, yeah. But here, let's get into Algebra 2. So each of these standards, so when you take, let's imagine you're a 10th grader in Iowa, you have to take the ISASP in math, and you get a math score. Well, it turns out if your item is math and it's at the 10th grade level, it makes sense to call that math. But the reality is the blueprint is made up of standards. It may even be substandards. These are the actual things that teachers are teaching in their classroom, right? We thought, hey, it'd be nice to measure these because if I give you a math score and your score is low, how do you make it better? Do more math is the answer, right? But if I give you a score on, let's say, the curricular standards of the real number system, quantities, complex number, so forth, and one of those is low, then you know which one to go work on, right? So what I'm arguing is that this set of standards, if we made these latent variables, each with a score, each with a set of items that measure specifically that's a more fine-grained or narrowly defined concept than 10th grade mathematics. And when you get to those fine-grained concepts, I think that's where you start to see items that you have to have multiple factors load onto. Or the item has to be measuring multiple factors. In particular, it's really hard as you get further in math to isolate a concept in algebra without having algebra 2, without having algebra 1 involved. Or geometry. Or if you think about, like I took calculus, and I don't know how many of you have taken calculus, but in my calculus class, the professor always said, well, like when you're in pre-calculus, what you're really learning is algebra. And when you get to calculus, really you're learning what the pre-calculus stuff is, right? Sort of the concepts. And if you think about progression in math, like a calculus concept might be like take a simple derivative of a simple, like what's the derivative of x squared, right? Well now, okay, what's the derivative of x plus 3, the quantity squared, all right? So now you have to think about chain rules, all these other things. But what you'll do is this much, like this little fraction of calculus to get the derivative, and then all this algebra to simplify or otherwise solve the problem, right? So the argument I'm trying to make is that item, if you're trying to assess a calculus skill, has to control for your skill in algebra. If your only way of analyzing it is correct or incorrect, right? So why, in the past, a multi-factor item was bad was because our tools were not so precise. Now our tools have gotten more precise. Our theory can get more precise too. Not every theory is that precise. I agree with that. But I think conceptually, the more narrow the standard gets, the more important it is that you allow for other dimensions to load on it. And that's where the latent variable interaction can come in, because if you think about the latent variable interaction now, let's imagine I have a number that involves something with a real number, something with quantities. Okay, if it's a problem where you have to be good on both to have a chance, like you have to know a bit of quantities and a bit of number system, that would map entirely onto this first line right here. Because if you know a lot of both, this interaction goes up, but any one main effect doesn't increase what you have at all. So that is why a latent variable interaction is an important term, but our methodologies actually outstripped our empirical sciences to know where we need to put it. So there's an answer, long-winded answer to your question. How's that?
And that specifically is like what's up for debate right now? Is that
No.
you can do that or you can't do
No,
that?
the psychometric world is full of people who debate almost on a theological perspective. So I had a colleague once, sorry, this is too much, but I had a colleague once, he used to be in the seminary, and he's now department chair at a different university. Good guy. And I remember we were having a conversation about academics being entrenched in thought and whatever, and he's like, you should see what it's like in the seminary, because everybody thinks they have God on their side, right? And there's no amount of evidence, and there's no amount of theory, right? Okay? So, and I kind of feel that way with psychometrics. I know this sounds terrible, but I kind of feel that way about psychometrics. We don't observe F. Right? So everything we're doing is some approximation for it. And it's like saying, well, God only wants simple structure items which has one dimension on it. Right? Or, and again, I'm using God in the, I'm sorry, is this too much? Everybody's laughing, but.
No, it's just your example of all thinking they have God on his side is just like very vivid.
Yeah.
I mean, but you can see where that's going, right? This were his exact words to me. I kid you not. And I had never thought about that perspective. So what the debate is, I would say, is this. In psychometrics, it's not a debate, it's a focus of where your training was, right? If you were drilled into your head the methods of exploratory factor analysis, you're going to tell everybody that what I'm telling them is full of BS. If you get into a model-based approach, where you have a ability to go and build and construct and identify models and make sure they're statistically sound, you're going to argue differently. And the question then becomes empirically which one is valid. That's a model comparison test, right? I don't believe the other. This is why I'd love to have a debate, because I feel like I'm lacking an understanding about what I'm hearing about. This can't be. It's the same thing when it comes to. I talk about this current sort of debate in social science version of psychometrics over whether some scores are really parallel items models, or is there a model that underlies classical test theory? These are some of the philosophical debates that are happening in the psychometric community. They don't have to be, but that's what happens.
So just can I say that we don't consider interaction terms in confirmatory factor analysis because it violated the normality or something?
I would say that most software doesn't allow you to estimate them because of that. M+ will in limited quantities, but that's because it switches the estimation process to something that will allow it. So what I think you can safely say is it is much more complex to estimate a model with a latent variable interaction.
Would Bayes let you do that?
Yes,
Okay.
Bayes will. Bayes has other problems. I know I have to say it.
Everything has problems. Which problems do you want to know?
Guilty is true.
The Spirit Airlines.
Yeah, the Spirit Airlines of this semester. This is the Spirit Airlines of SEM right now. That was your SEM class. Well, you know how Spirit Airlines was, right? Yeah, we had to pay him to talk. Yeah.
We did get seatbelts.
You got seatbelt, and I will admit that the restrooms are free because I'm not going to go down that path otherwise. Wait till the university monetizes those, though.
Oh.
We've got parking. No, I'm just kidding. Don't talk about that. No, I'm sorry. Hey, we're all in the same boat on this. It's not like I'm making those decisions. I promise. I'm the radical that thinks the university shouldn't charge for parking for their faculty and staff.
Yes,
Right?
though.
Because if you own the lots
Yes.
and you have the ability to actually do it, what you've just done is put a tax on, and some people's salaries.
Attendance.
Right. Some people's salaries are lower than others, but if everybody says the same thing, it's now a regressive tax on your faculty. I've worked in some other terrible jobs where they didn't own the lots, and I had to pay someone else for parking. Like I was in college, downtown Sacramento, having to pay for parking for a job that I had to work at least 2 hours just to pay for parking. Right. That was a bad idea. That was only a 3-week job, and I realized that was not going to fly. But point I'm trying to make is, I'm the radical that thinks we shouldn't do that, but wait, you wait. We'll monetize the bathrooms here. Maybe they'll be clean that way.
They do in Europe, don't they? Or
In some public restrooms.
Some.
Yeah. Train stations and some definitely do that. Maybe more than some. The ones I've used are the train station ones tend to have it, but they're clean.
Hey,
But anyway, all right. I just took us off a big tangent.
sorry, that's my.
No, that's good. I'm glad. I'm good. I wanted to talk about latent variable interactions. I didn't know where to put it, though. That's good. And it will come up again when Aegon gives her presentation, so it was a really good question to tie into it. So, anyway, yes, I'm acknowledging differences in the field also as I go, and I'm trying to do it with respect for people who may disagree with me. Trying to, even though I'm right. That's right. God's on my side on this one. But actually, that's the thing. I would like to argue that God's not on my side. I can go and use theory and evidence and mathematics to go and say, this is allowable, this is doable. The question is whether it's true of the universe or of the world that we observe, right? And that's a different question than it should never be, because someone told me that back in my first class. So that's all. It's putting the PH in the PhD, the philosophy part, right? Yeah. So anyway, yeah, just think about that when you argue with someone. It could be worse. Okay. Finally, so we found so far in this model doesn't fit by likelihood ratio test. The independence model likelihood ratio test, there's some correlation in the data. So we know there are factors that may be here. It doesn't fit by CFI. It doesn't fit by TLI. It doesn't fit by RMSEA. The SRMR of 0.079, again, I don't know how, I don't care about that.
That one, the 0.05.
That's the weakest one. It's supposed to be 0.05, but it's the weakest of all because it doesn't have a good standard. So, and then we can look at results, but we really shouldn't look at results here because these results are for a model that doesn't fit. And if we were to fix the model fit, the results may change. So let's keep going then, shall we? Okay. Well, I do have the results here. I'll make a little bit of a point of results. Where are the things, right? First, factor loadings. Your factor loadings. Oh, you know what? I like this. I can turn sideways. Let me try this for a little bit here. Factor loadings show up in the latent variable section. Right? And that is where you can see it because you see the sit equals tilde. That is the syntax for it. So each of this is the estimate column is the unstandardized factor loading. The standard error is right next to it. That is the standard error for the unstandardized factor loading. The z value is simply estimate divided by standard error, just like in path analysis. We call that a Wald test. That is testing whether or not the number in estimate is equal to 0. As a hypothesis test. The null hypothesis being the estimate is 0, the alternative is it's not equal to 0. Okay? And then the p-value associated with that z. But now remember, a z, that's your indicator. This is literally looking up a normal distribution. Like it's the area to the left of the curve of 17.096. So it's very, very tiny. Then we get two columns, std.lv and std.all. And this is where the distinction comes into play. std.lv would go and standardize the factor for us and give us the value of the factor loadings if the factor itself were standardized, meaning the factor had a mean of 0 and a variance of 1. But you'll note these numbers are identical to the estimates. And that is because
We told it to be
we
one.
told it to do that. So std.lv is the model that we just ran. Right? Does that make sense?
So is this where if you put the 100, maybe the estimates would like 123, but the standardized would be the 1.23?
Yes, that would be it. And if you'd like me to try that, let me get through this and I'll do
No,
that.
yeah, no, I just.
Yep.
Can you just say one more thing? What you said, and I forgot the second half, is std.lv gives us what the loading would be
If the factor were standardized, meaning we
Thank you.
set the mean of the factor to 0, set the variance of the factor to 1, and it just so happens in our syntax we did exactly that, and that is why right now this column is identical to the estimate column. Yes?
And when will we use data Y? The std.lv versus the regular estimate?
std.lv is great if you have, so each of us sort of, it comes to factor analysis with a little bit different tradition. I come to it with a standardized factor mindset because a lot of the training I've done was in about how do we give people better scores. Whereas other people are like, no, I want the marker item. So std.lv is like translating among common languages, like bilingual, right? Being bilingual. Let's put it that way. I'm gonna try an analogy. We'll see if this works. You're in Canada. You're in Quebec, and one of you speaks English, which is the standardized latent variable, and one of you speaks French, which is the marker item. That gives you this, basically gives you an understandable, it's like the street sign being in 2 languages.
Yeah, okay.
How's that? No?
They don't actually speak true French.
No, it's French Canadian. It's French Canadian. But do we speak true English
So
here in the United
would
States?
Would it be also like possible to use that, for instance, that our items are not scaled the same?
No, that won't change,
Okay.
right? What does change? I'll give you another one. Okay. If you run this model and you put a marker item for sit 1, this becomes a 1. These numbers change, but this is always going to be the same. Okay? If I run this model and I put a marker item on number 6, those numbers change, but these are always the same.
They're talking about the standard.
That's right.
Distances, okay.
Yeah, so the marker item approach, you may pick a different item to be the marker, and that causes all the estimates to change for the other ones. Whereas std.lv doesn't use a marker, so regardless of the model that you use, they will always be the same. Okay, std.all talks about the standard, this would be what we call the standardized loadings, the standardized parameters. This is now saying what would happen if not only we had a latent variable that was standardized, but our item had a mean of 0 and a variance of 1 also. Right? This is the version of the standardized coefficient that would be similar to that of the path analysis, where we have the standardized coefficients. So these, for single factor models like this, are an incomplete index, are very close to what R squared would be. Or actually, the opposite of right. So, here. Do this real quick. Yeah, not quite. Anyway. So, once again, what the std, I was looking to make another connection, and then I should have practiced. I'll come back after break to give you that. Okay. So what this will tell you is, this is basically the correlation between the item and the factor. That's what that happens. Okay. Now we get into intercepts. The item intercepts again, all the columns are the same. Let's first talk about the estimates. Here you will note that these estimates, if you go back to the means, the top file, should be equal to the means. Why that's the case is because we had a standardized factor, And in the case of the standardized factor, the item intercept basically becomes the item mean. The other thing I'll note here is the std.lv column here is helpful because that is, I just said if the standardized factor we used, we would get the mean. What you should see, this column should yield the item means always for you because that's the standardized factor. It just so happens in our model we used it, so the estimates are the same. But when you look at the item intercepts, those means should be standardized factor. And then finally, std.all here is relatively meaningless. Right? So I don't even, yeah. And then finally, the residual variant or unique variances. Residual, if you come from the linear model perspective, unique if you're a factor analyst. Here what you'll end up seeing is the variances estimate again. The std.lv, this will, now these will never be equal to the variance, right? These are, this plus the squared factor loading gives you the variance. So std.lv is less relevant here. And then
But there's your 50% that you just got.
that is right. So what was throwing me off was that r squared estimate for the first item is 0.54, which really should be that number. Oh, I get it. My numbers are different down here.
You had a .707.
So why do I have 0.707 here and then not up in my table? Oh, I copied and pasted in one part, but not another. It's 0.735. So this is what I was trying to tell you. If I take 735 and square it, I get the r squared for that item. So going back to the loadings, the standardized.all loading, if you square that, you get your r squared in a single factor model. And why it's in a single factor model is that there's only one loading per item, so you only have one of these to worry about. If you have an item that measures more than one factor, that's not true. Now you have to worry about the contribution of the other factor to the r squared, and that won't do that.
Let me ask you a dumb question.
Yeah.
But when you said that, I'm looking across them, and if you square them all, I think it's going to be more than one. So,
Oh, you mean these right here?
yeah.
Oh, no, I'm saying each one, square each one individually,
Okay.
not the sum.
So they should pull up. Okay.
Individually, that's right. So think of it this way. If you want to know how much variance is accounted for in the first item by the factor, it's this thing squared. That's it. Okay. Now that's a weird topic in the first place. How much variance of the item am I explaining by the thing I didn't measure? That's weird. And if you really want to make Lisa's head explode, now none of you are in her class except for Michael, right? Is anyone else taking a Lisa Hoffman class this semester?
Erica has a TA. So.
Can I ask you both to do this for me? Can you raise your hand and say, why is it in one class you give me an r squared for an item that includes the latent variable, but in multi-level you don't?
Well, we have a head left.
So interestingly, now do it. See what she says. Put her on the spot. Say, Jonathan made a point of this because this is basically a multi-level model. The factor is like a random effect. And I'll give you what I believe her explanation will be, is you can't go and say that you've explained variance just because when you didn't observe it, except for in the factor analysis part where they do that openly and willingly. So this is a difference in field. If you're in multi-level, you can get an r squared that includes the random intercept. Once you control for the random intercept, your r squared gets much higher. But because you didn't observe your r squared, your random intercept, the multi-level field says that's kind of cheating. You shouldn't report that. But that's totally okay if you're in a factor analytic field, and notwithstanding that the factor analysis, oh, by the way, is a multi-level model as well too. All right? So, there. Will you report back to me in a couple weeks? Actually, she won't be here next week. Tomorrow she'll be there. If you're there tomorrow, could you just you don't even report back to me. You can report for the class. I'll hear it tomorrow. For those of you on YouTube, do me a favor. email lisa-hoffman at uiowa.edu and ask that question. Go to the YouTube transcript.
I feel like mom and dad are fighting.
Mom and dad aren't fighting about this. I don't have an answer for it. It's funny because I'll give you the backstory. When I first met Lisa, my multi-level knowledge was not what it is now. She did train me a lot in multi-level. I actually never took a class in multi-level in grad school, go figure. But I knew factor analysis, and I knew this. So when I started doing work in multi-level, I started reporting R-squared with the random intercept. And she's like, no, that's cheating. And I'm like, the hell is cheating? That's what we do. And she's like, no, it's not what we do. I'm like, oh. But we're doing the same thing? Well, mostly. Okay, yeah. But
How's it cheating?
Exactly.
It's like putting the ball through the hoop.
But you understand what you're thinking, what we're thinking about here. This is, if you were to observe the factor, we could say it accounts for this amount of variance in each item. And that number is 1 minus the unique variance also. So if you're looking at 1 minus the standardized.all unique variance, the standardized unique variance. Okay?
Cool.
There we go. I'm sorry for wasting all your time with these stories.
This is good stuff.
For me, you're sorry too?
No.
Oh,
You're doing it. We're all are.
okay, I hope so.
Something to speak the whole time.
Well, I want to give you like the flavor of where you will hear it like when what I'm trying to do is tell you how to do it, but also like, oh, that's a thing I believe, or that's a thing the field believes, right? Because when you step out of this class and you start looking at other people, they're going to have other beliefs and other ways of describing it. So I'm trying to prepare you for that as well too, but with my opinion, of course.
We do it the right way. Because
God's on my side. And by God, I mean the factor that we call G, right? Yes. That's right. But some would argue that math is God because we discover it, right? It's just, anyway. No. I'm not trying to make light of God. This is a small g God conversation, not the... Maybe not. I'm just digging a bigger hole, aren't I? I'm not trying to make a value judgment as to which God you should or shouldn't believe in. Let's put it that way. I'm talking about the...
But we should believe in factor analysis.
Yes.
We're here. That's like bare minimum for enrolling in the class.
Yes. Now, I would say this. Believe in the mathematical procedure of factor analysis, but also don't put all your stock into believing that this is the right thing. That's what I would also say. What I mean by that is, look no further than like intelligence, like how we assess intelligence. You take an IQ test. Is that, somebody who scores high on that, are they really an intelligent person? Perhaps.
There's nothing to taste.
But that only covers the domains in which that is. Now the IQ folks, at least at the beginning, would claim, fluid intelligence is everything, right? And then that's sort of been argued against and so forth. But the point I'm trying to make is, do believe in the process. I think we have a mathematically rigorous and sound process of doing data analysis. Always question your factors, always, right? Particularly as the world changes. These things change, right? They don't exist. So does that feel better? Now I feel like I put everybody sad here. You were telling me there was this deity that was this factor, and now you're like, don't believe too much in the deity. You're like, okay. I'm saying that hold out rational thought that might not be the only thing that you're describing with your deity. That's all I'm saying. Fair? It's like a religion that's like, yeah, but we could be wrong, right? Which one says that, right? I don't know. Me, that's my religion. Yeah, I could be wrong. Anyway, the scientific belief in that this is what we think to be the best of our knowledge today may not always be the best of our knowledge going forward. There, how's that sound? This talks about standardized modeling. Let's talk about this. This is the section where I describe you can shorten the Levon syntax. This is all you need. You're like, Jonathan, why you give me so that much? And if you add that to the SEM function.
Just to say that you're switching your function with your processing.
Right.
Yes.
But here everything is the same. These numbers are all the same values. I remember 0.195, 0.079, etc.
Good stuff.
Okay, how about we look at what happens when we go and do the marker item here. Right? Factor mean zero, factor variance estimated. Oops. And here, I gotta check something, because there's something, yep, there it is.
You may sit like
Yeah. Okay. Sorry, I saw the word standardize equals true, and I thought that was std.lv, but that's not the case. When you run the SEM function, and you do not otherwise specify std.lv, it estimates a factor mean of 0, but it fixes the factor mean of 0, pardon me, but it estimates the factor variance. And it does so by taking the very first item defined on each latent variable and sets its estimate to 1. And the nice thing about Lavon, if you compare to M plus will continue to have a 0 standard error and a z-value of 999. At least in Lavon, they blank that out. That tells you that this is a fixed parameter. You set that, or the Lavon set that. It's not an estimate. So there should not be a hypothesis test. But when that happens, you will note several features. The model fits the same. 0.195 for RMS, I've just highlighted that a second ago. And 0.079 for SR-MR. If those two are the same, you can just assure you that all those other numbers are the same as well too. Okay? Let's take a look at the estimates of the factor loadings. Now, the first item's factor loading is a 1.
Right.
The other ones have changed.
But the right-hand side did not change it. Oh, you said that they should not change, correct?
These will not change on the right-hand side.
Right.
These aren't changing, so what std.lv should give you the estimates that we saw in the output from the first model, and std.all should be the same as std.all in the first model. And this is the same, but what we found here is the factor variance estimate was 1.734, and that estimate is a part of the first item itself. Right? So you have to think about it. The first item is the actual variance, not the estimate here. But the variance of the first item, what the model says the variance should be, is factor loading squared times factor variance plus unique variance. Well, the factor loading for this first item is 1. The factor variance is 1.734. Unique variance is 1.475. So if you multiply these two numbers together, you should arrive at the variance for the item. And I'm not going to do that, but I'm going to assume that's the case. Actually, maybe, should I do that? If I'm wrong, I'm really going to be mad.
That's right.
3.29, that should be right about what that is.
That looks very close.
Yeah, where did I go?
That, there.
Oh, that's not it, sorry.
Look at the calculator.
Yeah, me and my calculator.
It's like 1.734 times 475.
Nope, that's not right. All right, well, I'll get there.
I was gonna say, don't forget that I think some of the outputs on the different.
Yes, my
wrong,
outputs, yeah, I had
so-
copied and pasted and didn't fix it, so yes.
I need to set a seed.
Yeah, that's not just setting the seed.
That was the sum.
Would that really matter?
The sum of them.
What you
Oh,
showed
the
us
sum.
was the sum of
Oh, the sum, pardon me, the sum. That should be the sum. You're right.
Setting seeds,
Oh, my goodness.
I'm looking at my numbers. I'm
You
like,
know
what's
what?
the sum?
That's inexcusable. That's the sum. It is the
And
sum.
That's what showed up
It's
above, yes.
factor loading squared
Wrong
times factor variance plus the unique variance. That is the sum.
So it was like a 1 times this plus that.
1 times that. So to get the other variances, we'd know their factor loading squared times this, and then add the unique to it. But you'll see nothing else has changed. Okay. Let's see here. Move on down.
There's a song with that.
What was there?
Move on to the line.
Oh, that one. That's been a while. We can also, I'm going to show you we can estimate a factor mean. And now in this example, I have to use, well, I can do here. Here, to make Lavon work, in the SEM function, I just add the factor mean, the name of the factor, tilde 1, to estimate it. Right? I had, the SEM function is trying to standardize the factor, but when I go and put a factor comment like this or piece of code in the syntax, it overrides it being standardized. So to answer your question, the syntax wins, not the function.
Why would we do this?
Why would we do this?
Yeah, it's the
Great question. If you ever find yourself in need of a factor mean, that would be why. So for instance, what's that?
we need it. Sorry.
Yeah. Well, do you have two groups of people who have different amounts of forgiveness? Right? Because how would you be able to tell? So let's imagine, now, to get to that answer, there's a few other steps called measurement and variance that we got to assume, which we'll get to after the test. But think of it this way. Let's imagine our study is we want to compare university faculty versus university students and their ability to forgive. And you created this 6-item scale. If you didn't know factor analysis, you'd add up everybody's sum and you'd do a t-test between it. But because we know factor analysis, we may want to get an estimate of the mean in each group. Or better yet, we might want to predict the factor with which group a person is in which case that would give us a factor mean difference. So there are cases where we would like the factor mean. Pretty much every time that you think about taking the sum of items and using it is where we'd want the factor mean. How's that sound? So what happens when we estimate the factor mean is somewhat interesting. Our item intercepts change, right? We fix the very first intercept to 0. That's our marker for the mean. We estimated the factor mean is 4.43. And now, these numbers have changed. But the factor itself, if I had picked a different marker item, and actually that is where, here, that's the other thing you have to do. You have to set the intercept to 0. Now, here is where, I should have done this with the variance as well too.
So in a way, did you make that like a reference item?
It's kind of like the reference, yes. Hang on one second here. Estimating factor means is what it's called. There we go. Let's imagine I change the marker item from 0 to the second item. I'm trying to do this in a way that doesn't wipe out my syntax, but there we go. Okay, when I do that,
You also need to like change the coefficient in the equal
in what? I'm sorry?
like after the equal tilde is the one multiply. Like
Where?
One.
Oh, this, so interestingly, in the equal tilde, that is for the variance. That is the factor loading. So if I change this, it'll change the factor variance. What I'm going to show you though is if I change the marker item for the factor mean, the mean of the factor will change a lot. I'll show you for the variance in just a moment too. But let me start there with the all right, so when I do the second item as the marker, now my factor mean is 8224. Before, it was 443. So now this is the problem with factor means.
Excuse my business. How are you communicating to R which one you want to be the marker?
To do this, to estimate the factor mean in Lavon, it takes syntax. Number one, you have to define, you have to basically put an intercept on the factor mean. But number two, on the intercepts themselves, you set one intercept to 0. And that will do it. By setting it to 0, it does not fix it to a value. Actually, it fixes it to that value of 0. By setting it to 1, it actually estimates it. It's a syntax problem. But think what I'm trying to actually talk about here is the concept that if Michael comes along and uses the first item, he says the factor means 4.43.
If I come along and use the second item, I say the factor means 8.244. Who's right?
Both.
They're equivalent. They're equivalent models.
Because when you start adding things up, they come to the same values.
Because the scale itself, basically our factor is a bunch of people ordered. Once we define its mean and variance, then we can talk about the relative size or the distance between people. But because we picked a different item, we get different numbers. Now let me show what happens with the variance, okay? Where'd it go? Come on, Jonathan. So I change this first item to the second item. Now our factor variance is 1.8089, whereas before the factor variance was, here it is, 1.734. So this is a weird thing to think about. Is it weird to you? Does it feel weird to you? I know we're on a break. Give me just a couple of seconds here.
It is weird because you look at, I know we talked about how the STDLB would be equivalent but it's not.
Right.
So it's really like hooking me, like why?
Everything, so it's all relative, is what I'm trying to say. Once you define a marker item or not, the model shifts all the other parameters so that the same inferences will be made. By inferences, what I'm talking about is if you give people a factor score, if you compare two scores, they will be the same distance apart, just on a different scale, right? You'll say one person has more of the trait than the other. Similarly, the items will all have the same configuration of which loading is higher versus lower. But at that point, let's take 10 minutes, think about how weird it is, and we'll come back with some more weirdness when we get done, all right? Keeping it weird. We're back at it. Okay, so again, the point I'm trying to make is that there is no factor. So whether we marker item or standardize, these are different ways of saying what the mean of the factor happens to be. If there is no wrong answer to doing that in just a purely measurement model perspective, the cases where it starts to become harder, there's two I can think of. One is if you pick a marker item that has no relationship to the factor. Now you're taking a loading that should be equal to 0, inflating it to 1. That causes a bunch of instability in the system. Oftentimes you see non-convergence. So if you get non-convergence with your data, the first step to me, if you're using marker items, is to make it a standardized factor or change the marker. Because the marker is just our way of cheating and saying, I don't want to give a numeric value to the factor mean. I'm going to take a little bit from data, or the variance. The other place where it matters is if you want to predict the factor. And this is where I'm going to take us back to September for just a moment. And remember my semi-controversial statement that we had the relationship between marital status and happiness, or feelings of happiness. And again, that was not me, sort of a tongue-in-cheek way of saying, make sure your model's right before you run off and get married. Life advice from me, right? I've covered all the bases today. Don't argue with people who think, a deity is on their side. And anyway.
Or just use that logic and make math your own.
There it is, right here. In this case, in this model, we have happiness being predicted by marital status. When the factor is an outcome, and when we describe its variance, this variance for the factor is now residualized, meaning it's what's left over after we predict it. But if we use the standardized factor, where this variance is set to 1, it can't move. So point number 2 where this becomes important is you need a number there that allows it to be estimable to then have a reference to be able to say how much variance is accounted for in the factor. Do you want to see the syntax for this model that I did before, now that you have a little bit of knowledge? This is kind of impromptu. Do you want to take a look at it?
Sure.
All right. Oh boy. What's that?
We're looking at the same piece of output almost the entire time we've been in class.
Yeah, I know, it's been a lot on the same thing. Sorry, too much.
No, I think it's kind of interesting.
Well, I'm over here apologizing, but there's a lot to it. I just want to, because it's so much, when I start to ask that question, what's this mean, what's this mean, what's this mean? That's my indicator. I'm like, oh, you got to think about what it is, slow down, let's talk, let's get the basics, because these are really important. But here, this would probably help if I'm in RStudio, right? I started using VS Code a little bit more recently. You ever used VS Code with R?
No.
It's pretty nice. Oh, no, that's not it. Give me a second. Tech Shop. I don't want Tech Shop. There, RStudio. Okay. This is me simulating data. There's our data. So model number 1 was just us without the factor model. Let me get to the factor model though. The factor model looked like this, right here. So happiness was a factor. It was defined by items 1, 2, 3, 4, 5. But happiness is then being predicted by Mary. Right? So this is like basically once I define happiness in my syntax. By the way, I'm teaching you SEM right now. Right? Once you've defined the latent variable, in the rest of your model, it shows up as if it were observed. Right? So this is like if we just
did not reverse those 2 lines of code.
Oh, I can actually, because Levon will look at the whole thing.
It just reads and uses.
Right, but conceptually, you think about it this way: I have to define what happiness is because it's not my data set.
Right.
But then once I've defined it, I can use it as an outcome. And in this situation, I need happiness to have a variance that can shrink. So let me run the model as is right now. Let's inspect it. Let's do this. There we go. Oh, did I type those in wrong? R squared equals true, standardized equals true, fit.measures equals true.
Oh, that's right, you're on model 2.
I squared. Sorry, thank you. You said the D. Come on, Jonathan. There we go. Okay. Here we go. And let me fit this with MLR so it looks the same. This is me doing things that you should never do in teaching, which is
Do it on the fly?
on the fly.
Yeah.
But for me, I love it. So let's evaluate this now like we just evaluated everything else, shall we?
Yeah.
Question number 1, does it fit? What is this test statistic once again? It fits the saturated model. By the way, this is the only time you will see it because these data are simulated. So I can guarantee it fits because I generated these data to fit this model. This tells us there may not be a correlation. Our CFI and our TLI are above 0.95. So we're getting a good, RMSEA is close to 0, and SRMR is very low. And we have all our estimates here, but let's take a look. We can tell that happiness is estimated with a marker item, with a 1, right?
Uh-huh.
And the variance of happiness is set to 0.078. So small variance, but there. And when we do that, we can say that we explain 7.4% of happiness by marital status. Okay? Now, what would happen if I did std.lv? Now, once again, that R squared is 0.074, so it's still the same model. Your variance of happiness now is 1, but the parameters have changed. Right? So now, what has to happen if we go up here to where we were before? I'm going to grab a screenshot real quick for our factor loadings. This is what they were before. Sorry, you can't see that small. There we go. And here's what they are now. These numbers have to change, right? So when you put in a latent variable and you want to have it be an outcome, a marker item is really helpful because now you don't have to say, wait a minute, why are my factor loadings different in one situation versus the other? Because the factor loadings are the only things that can change. The regression slope can too. So it's hard to see what the residual variance of happiness would be because in both cases, like happiness, the variance is 1 after you predict it, and if you didn't predict it, the variance would be 1 before. So why we have marker items is because we may need residual variance for factors. How's that? How are we doing with this example? Do you like the example? But now you've just learned the rest of class. The rest of it is nuance. So now you know SEM. You want to quit?
No.
No.
I still don't think I get CFA quite yet.
It's okay. That's why we're going through it, the pace we're going. And not that it's slow, but I just want to make sure it fits. There's value to be received from it. Okay. Okay, this is the rest of this example just describes the model fit statistics and what happens. It shows you the independence models, it shows you everything else. But why don't we get down to the part that really matters? We should look at the model. We know this model didn't fit. How do we fix it? Let's think of it that way. The modification indices are nice. However, one thing I didn't do ahead of this that I should have done, let's see here. Nope, that's not it. I'm going to go back into my code for path analysis because I want to put in the code that looks at the normalized residuals. There it is. I just always forget the exact Lavon syntax. And by the way, when I ask you questions about syntax on the test, it'll only be the quote, the stuff in the quotes, like what's an equal tilde. It will not be the options in the function. So, but here, okay. And now I'm, I actually, this is the only class I ever taught with Markdown because the code gets so hard to like.
I do think you've included the normalized residuals for inter-item covariances. Is that what you're looking for?
Yes.
It's just a little lower.
Oh, it is?
Yeah,
Okay.
it's included.
Well, how about I put this here then? Because I really need it there. There we go. Okay. So normalized residuals tells us where our misfit is really bad, right? Lisa makes a point, and actually people make a point. The positive ones mean we need to handle those more than others. But here we have a normalized residual between sit 2 and sit 6. We have one between sit 4 and sit 2. We have another one, this is sit 4 and sit 6. Sit 2 and sit 4. So the three biggest ones are sit 2, sit 4. Sit 2, sit 6. And sit 4, sit 6. You notice anything about those three items? They're the absence of reverse coded, but you're right, that's it. Those were not reverse coded. So this is the part I was talking about before when we think about the coding. And we'll talk about that as we go forward. But one of the ways to fix this is to go and say, I have a method factor that really reflects reverse-coded items. That factor itself may be uncorrelated with the other one, the actual factor of interest. In fact, it should be. It should just be a coincidence if it weren't. But now, once we identified that, we go to the modification indices to see how we could add it. And here, are our modification indices. Yep, here's the sit2, sit4, sit2, sit6, and sit4, sit6. Those three are there. Now we still have a sit1, sit3 that shows up. That has a normalized residual that's positive as well, but smaller than the other two. So in looking at this, what would you do?
I would say the evidence points towards a method factor, for sure. Especially because that's the only one out of the reverse coded items, and if you look at the normalized residuals, it's elevated, but if you think about the z value and the critical value of z, I think is like 1.96. It's just like a little over there, and everyone else is like, hello.
Yeah, that's, no, I think you're right.
Terms.
So what a method factor is, we'll have a little bit more discussion of this later, but we had a little bit in the slides. Is this, we could set up two different factors, although this doesn't get us where we want, where we have a positive and a negative. And if we do that, what's that? Sorry?
These like positive and negative worded items?
Yes, sorry.
Okay, clear.
I'm so sorry. I think Lisa used the word valence.
Yeah, valence, yeah.
Yeah, so positively worded versus reverse coded or negatively worded items. Yep. So here, when we run this model, let's take a look at model fit. Okay, now the two-factor solution. Look at our test versus the saturated model. Look at that p-value. This is real data, man. This is good stuff. I don't know who man is. Yeah, real data. Class. Sorry, if I was my son, it'd be, bro, this is real data. We're going to start every sentence with bro, right? Is that how it works? Bro, look at that. Somehow, by the way, when I pretend to be like that, nobody likes it. I don't get it. I think I'm hilarious, but it just must be really terrible. It's like nails on the chalkboard. I'm not going to do that. Yeah. All right, but seriously though, it fits. Fits a saturated model. If it fits a saturated model, you're going to be guaranteed that the other ones are going to fit as well too.
Is this the only way to go about making a determination though? Like I feel like it was something else we talked about before. To like see there's multiple factors.
So there are some other strategies. Yes. One would be to add residual covariances.
If you think about like the original assumption of factor being 1, right?
But the problem...
Or like only having one factor, excuse me.
Well, the original assumption should be that the covariance between any pair of observed variables is fully described by the things measuring. And so when we have one factor, what we're saying is that one factor is the reason why these two variables have a non-zero correlation. Here, clearly there's leftover correlation, so the factor is not the only reason.
Mm-hmm.
But when you add a residual covariance, you're basically acknowledging the factor does not do the work it needs to do to account for everything. So you've weakened your validity argument to me. Right?
Is there a world in which that pays off?
Like pays off in which way?
Like adding the residual covariance, even though it goes against like the assumption of like the factors explaining it. Like, is there a trade-off there? Or like if you're doing factor analysis, you really don't want to mess with that?
There is a trade-off. I mean, certainly you can add those. People do add those. I don't know that people make the argument as strongly as I do about the validity part of it.
Okay.
That's why I truly believe model fit is about validity, right? That's literally a quantitative validity argument. But the other part is you add it, what happens? Turns out, and we'll see it here in just a bit in the handout, when you calculate reliability, if you calculate reliability more correctly, that residual covariance counts against reliability. So if you're really trying to measure something, what's unaccounted for has now should become error. I'll show that in just a bit. So that's the Foley z-score two-factor model. But the problem I have with the two-factor model is this. I was trying to measure situational forgiveness And now I have a positive forgiveness and a negative forgiveness factor. Aren't they the same thing? How does that work out? Right? Well, I think another approach that may have worked could have been the following. If I just did situational like this, and then I said this. So what did I just do there? I'm going to create the situational forgiveness factor as I have done before. All items measure it. But I'm going to create a method factor that notes this method factor only loads onto the reverse coded items. That means this factor would be someone's propensity to have that reverse coding cause their score to change. It's a weird way to think about it, but if it's a factor, it's like how someone reads the negation and then interprets it and provides response.
You set to a variance of 0.
But this, I think, there's nothing about how a person observes negated items, negative valence items, that should be correlated with the factor itself. So this gets into a part. Well,
I'm sorry. It should be correlated to the other factor, or
no. I mean, like what? Like if you're really measuring forgiveness,
yeah.
What sit n really is how negation causes you to change your score.
Got it.
Well,
Okay.
to me, that's not necessarily related to situational forgiveness. That's just you reading text, right? So I think philosophically, a method factor shouldn't correlate with the factor of interest.
So our full factor is sit, right?
Yep.
Yep. And okay, I think I was having a moment. I was reading sit p on that factor for some reason. I don't know how to
Don't worry about it. This is okay, but let me just show you what happens when I do this. The model fits, it still fits. It's not as good. It's still a pretty darn good fit. I mean, the RMSEA is 0, right? The standardized root mean squared residual is close to 0. But now what you can see is I've got a little bit better R squareds for those items because now, at least for these items, there are 2 factors predicting them. So it should be more, hopefully higher R squared. But for the original items, those loadings have changed because now I'm controlling for the negativity bias in the wording of the question. So what this model still allows me to do is come up with and preserve my idea of the trait I'm trying to measure, situational forgiveness. But this model is controlling for my negative worded items, is what I would say.
Could it be, and I may be putting my practitioner hat a little too much here, but could it be that those negatively worded items could be speaking to another phenomenon happening with the person?
Could be, yeah. It
So,
could be.
like what, from a fact that I can see a standpoint, right? Like, I as a practitioner want to see like maybe if there's any correlation between this person having like depressive symptoms or like negative cognitions that lean that way. But from a CFA standpoint, like how would you handle that, or would you do anything about it?
That's a great question, and I'm noticing that my microphone is not on right now. Give me just a second. Why does it cut out? Let's try this. There it is. It's back. Sorry for the missed. I'll have to cut that out of the video. But so to your practitioner perspective, the question was, what is it about this? So could it be related to forgiveness, you're saying?
Yeah, for me, those negative items could speak to other like the person.
Oh, absolutely. Absolutely.
Attribute their things,
Yeah.
they have their own negative attribution. Perhaps because they're depressed.
That absolutely could happen. And that could be related to some other trait. I'm just saying a couple of reasons for this. I'm going to let it be not correlated here, because if it's not correlated, it doesn't hurt me any, right? But if I wanted to let it be correlated, let's see what would happen. I mean, we could, in theory, make that work.
it still fits. And our correlation estimate is negative 0.17. Not, what's that? Not very strong at all, no. It's tough to tell. And in the absence of another experiment or another study, I don't know. But I will tell you that from a method perspective, having us only have one item where that correlation, having us have a method factor tends to have that method factor be uncorrelated from the factor of interest. It's more just controlling for what we're seeing in the data. If there's more to it than that, that's sort of outside of our scope of this study. I'm not denying it could be true. Yeah. It's a statistical method. Yeah. We have to control for it analytically. Otherwise, it can confound our results. I think I'll put it that way. Does that make more sense? Yeah. I'm sorry. Yeah, no, this is great. I'm really happy about this because I don't have the training you have. And so when you say, to me, it means this, I need that information. So I'd like to teach you. But in the stat world, this is purely a methodological artifact. It's like literally, if you think about linear regression, in a linear regression, we may have control variables, right? Well, sit1R, the model for it, is now being predicted by sit and sit n. So sit n is controlling for the influence of the negative factor on it. Now, whether it's correlated or not, by practice, method factors tend to be uncorrelated with the factors of interest. Doesn't always mean that needs to be the case. I think it's a safe statistical assumption to say this is purely an artifact of my survey and not a feature of the person. And the fact that it's negative, by the way, is somewhat maybe I'm suffering from confirmation bias there, but it's hard to find psychological variables that are correlated negatively. It's especially hard when you think these are both supposed to be about situational forgiveness, right? So to me, I leave the zero there, but yeah. Method factors? Pretty frequent, yeah. Mm-hmm. I think they're great tools. They really help build your survey into a better perspective of sort of rounding out the things that are interfering with your validity argument. But let's go back to validity for a second, though. What this model that I have on the screen here is showing is the following, right? Now, I cannot necessarily come up with another factor where the other three are on it very easily because now I have, they sort of have all the data put in all the factors. But what I can say is this: my original scale, the 6 items and the factor for it, is maintained. So I have if I were to get a factor score for a person, my situational factor would be comprised of their responses to all the items. But what's different about it now is that factor is likely to have, now I'm not incorporating the parts that were not that were due to the negativity or the negative valence items themselves. So basically I've controlled for it from the scale. I still get my scale. I still do it the way I had intended by building it. So does that help? Exactly. We're controlling for it. That's right. So if you're thinking about giving a person a score, you'd never give them just a score. I mean, you could give a sum score. You'd never give a negatively valent score to a person. It's a method factor. It's an artifact, right? It's a sort of a control variable. But you still could give the situational factor score as well. How's that sound? Interesting? It's different, that's for sure. Very what? Mechanical. All right, let me see if I can wrap this up. We got 20 minutes. One last thing I wanted to talk about was what we do at the end. What is that? Reliability. So for instance, we can estimate reliability, and it appears my syntax for this is based on the 2-factor version of it. I can't change that. I probably should have changed it ahead of time, but sorry about that. So what we can do, I did this for the two-factor version example because I wanted to make a point. Number one, last time we talked about reliability, I said reliability for what, right? And we came up with a formula called omega, which is the reliability for the sum score of that model, not the factor score, the sum score. Well, it turns out that reliability is the loading square for items that only measure one factor. It's loading squared. That's actually why, actually now my head's coming back. Why I have two separate factors here is the reliability is a little bit different when you have cross loadings on your items. So I can't as easily calculate it within code. So I left it this way. But here, it's loading squared over loading squared plus unique variances plus any residual covariances. But what this is doing is, I remember in path analysis, I had to label my parameters to go and do indirect effects. I put labels on all of my parameters here. The loadings have an L, the errors have an E, and then with those, I use that to calculate my reliability. So my colon equals is my defined variable. Yes.
Can you, the thing that denotes the label is asterisks. That's the label.
So it's a text. It's a text and numeric code in front of an asterisk in front of the variable.
Thanks. Okay.
That's it.
Great.
So what this does, though, is now at the bottom of my output, I get my estimates of reliability. So my reliability, if I only look at the factor of the positively worded items, it's 0.749. The sum score, not the factor score, the sum score. If I add those items up, their reliability is 0.749. If I do that for the negative, it's 0.780. But here we get a standard error with it too. I like that. It's kind of fun.
Is there any way we can centralize like the null versus alternative hypothesis would be omega?
No. Omega, so reliability is a descriptive measure only.
Okay. So we would just say that like this is what it is.
By descriptive, I mean literally it comes from a combination of those parameters, but the parameters themselves come from your model building process.
Okay.
Right? So does that make a distinction? I make that a little bit. The other reason why I want you to think about that is reliability is conditional on your model fitting. Because our model didn't fit before, what will happen is our reliability will probably be much higher for that single factor. Overestimated reliability. When model doesn't fit, reliability tends to be overestimated. Now, if your advisor said, what is this omega stuff? I don't understand it. Give me coefficient alpha. You could do that too. Coefficient alpha is the model where each of the factor loadings are set to be equal for a given factor. So here, to set my factor loadings to be equal, this is called a tau equivalent model, by the way. Tau equivalent has equal factor loadings, but unequal intercepts and unequal residual variances. But my factor loadings here are LP for the positive factor and LN for the negative factor. You have each of my unique variances uniquely estimated, but then I calculate the reliabilities again, and you'll see my reliabilities are darn close to where they were before. But these, if you were to go and put these data into any other package that did, oh, here, I've got it. This is the psych package. They have a coefficient alpha function. If I just look at the reliability of the positive items, its estimate is right about what my estimate was as well, too. And the same thing with the negative. So that's coefficient alpha. But what the interesting thing about coefficient alpha, well, I don't know if it's interesting, but the model fit has to be worse because you've just constrained the factor loadings to be equal. Now, it's not that much worse, but it does change it a bit. Finally, you may want to say, okay, I'm tired of the sum score. Let's give everybody a factor score. You can calculate reliability for that too. It's a little bit harder, but still follows the same premise, right? Reliability is the ratio of the variance of true score, which is basically due to the trait, over the total variance, right? The true score is just something, well, total variance actually becomes true score plus error. And how we quantify that is the following. The variance of the true score is really the variance of the factor. The factor is the true score. The variance of error is the squared standard error of the factor score. Because that's how much error there is in any estimate of a factor. Yeah. It's just very close to an ICC, isn't it? Yeah. Very close to it. But it's close to it. I wouldn't say it comes from a different place. But yeah, ratios of variances. Yep. It's related to F tests also, right? So in this case, the variance of factor, we get that from our model. We either set it to be 1 in a standardized factor, or we estimate it from a marker, right? The hard part is the standard error of the factor. Ignore all this. This was when I taught this before, Levon didn't have the ability to give factor scores, so I just wrote it myself. Yes, I did. I like that. And then I calculated its reliability that way. And the factor score reliability, so basically what I had to calculate was the error, the standard error of each factor score. So in factor analysis, if everybody gives you complete data, everybody's factor score, regardless of where it will be, has the same variance. That's the same standard error. That was what we talked about at the end of last week. That changes in item response theory. But in factor analysis, it's true, and we can see the following, that the variances of positive and negative of the reliabilities are a bit higher than what you saw for the sum score. That actually happens a bit in factor analysis when you look at the factor scores. What is right? What is wrong? Well, why is that the case? Part of the reason this is the case is because the factor scores themselves are called shrunken estimates. Right? To get the factor scores, I had to assume they followed a normal distribution, served like a prior distribution, which causes them to be pushed down, which shrinks both error and true score variance. And so that actually shrinks error variance for certain. True score variance may be fixed if I standardized it. And so you may see this to be a little bit higher. But one of the things that you don't tend to see is you don't really call factor score, you don't really use reliability as much. You tend to just look at standard error of measurement, which is what the output should do, but I didn't output it in there. So that's another thing we do. Finally, the other thing we could do is we could test the assumptions of classical test theory. I like that. It's the controversial part of this. But yes, we can. Because classical test theory is a parallel items model. This is not even testing the assumptions of classical test theory. This is testing tau equivalent versus congeneric. But we could do a likelihood ratio test to say, do we really want all the loadings to be the same on a factor, which is the alpha version of the model, or the loadings to be freely estimated, which is the omega version of the model? And in this case, a likelihood ratio test is conducted. The null hypothesis is the model with fewer parameters holds, and we reject that null hypothesis. So basically, we should not constrain those to be loaded to be the same. Technically, classical test theory is the Spearman Brown, the parallel items, where all the loadings and the unique variances are equal. Although here, yes, I constrained the unique variances per factor to be equal. So the reverse coded variances were 1.374. The regular items were 1.056. And in that case, I could still do, well, I can't actually do it. But then finally, we can look at the distribution of factor scores. This is what we ended up having. So this is the positive factor from that two-factor model. The mean's at 0, but you'll note it's not perfectly normal. It looks pretty good. But the point I want to make here is even though we may, and here's the negative factor as well, even though we have to assume, at least in the method I use to get factor scores, we have to assume the normal distribution. That doesn't mean they're guaranteed to be normal when we look at the EAP estimates. It's this is the updated version. These would be the posterior distributions. But that's a topic I'm not introducing yet. And then finally, this is the part I really love. Factor scores from parallel items model are sum scores with a different scale. Let's unpack that for a second. Factor scores. So that means if I run a model, a parallel items model, and get factor scores from it. What's a parallel items model again? All the load. So for each dimension, all the loadings are equal. All the variances are equal. Okay. So that's what that is. So if I fit a parallel items model and extract the factor scores, those are equivalent to sum scores with a different scale. So in our case, think of it this way. A sum score for sit P would be the sum of sit 2, sit 4, and sit 6. A sum score for sit N would be sit 1R, sit 3R, and sit 5R, right? The parallel items model here, again, has the same loadings for each. That label is the same across each. And so this is the sum score and the full CFA. Their correlation is pretty high, right? This is not the parallel items. This is the full congeneric, every parameter estimated model. So this is why people tend to say, well, yeah, I mean, I can give you a sum score. It's no big deal. When the model fits, my correlation with the sum score and the factor score is like 0.95 or better. It's a pretty good correlation. But here is why I say the following. This is the correlation between the sum score and the parallel items model factor scores. When do you ever see a scatter plot that looks like that? When math happens. What we're up against is a theoretical limit. That's what happened. And this is why the psychometric God is on my side. I'm just kidding. But no, what I'm saying about that is, see, I can qualify. Psychometric God, there's many of those as well, too. It's a polytheistic society as psychometricians. But that being said, why I say this is if you're given this plot and you say factor score, well, its mean is 0 and it's got a variance of 1. Sum score, its mean is, I don't know, like 15 and it has a variance. You could go from one to the other perfectly. If you knew the mean and variance of the sum score, you could transform a factor score onto that same scale. You've just changed the labels, but the relationship's not changed. To me, this is like when I saw this plot, I went back to I made this about 2015. I was like 10 years post-training. Like, I've been thinking about this wrong. I really have, right? But that's, to me, really interesting. What does it mean to you? When your advisor says, I need to add things up to do this, you probably have to add things up, yes. Should you? Probably not. But if we're making really educated approximations, this would be fine. But when you're adding things up, you're actually assuming all the loadings are equal. All the variances are equal, right? Or put another way, you're assuming if you look at the covariance matrix, all the entries in the diagonal are equal and all the entries in the off diagonal are equal. That's how we started by looking at covariances in this class. I guess we looked at correlation before covariance. But we could tell immediately that wasn't going to be the case.
But this also says every question is worth like an equal amount of points.
Mm-hmm.
So if you have like one question worth 2, another worth 4, this falls up. Or does it not?
I don't know the answer to that. I have to think about that.
If it's not nothing before,
Yeah, I think this does blow up. I think it does blow up. But yeah, this is equally weighting. Yep. Mm-hmm. But what you'll see, speaking of that, do you remember from last time when I said what matters in the calculation of the factor score? From a model perspective, it was the item information, which was loading squared, which you can't really see here, over variance. So if you wanted to say which question had more weight for the factor score, that's what you could say here. The parallel items model assumes each question is basically the same statistically. You can interchange it. The factor analysis model, where we're estimating all the parameters, does not. So when you ask the question, what if I didn't have equal weight to each item, instead of just sum them up, what if one counted for 2 times the points? Well, we're doing that now with the factor analysis. It's not the same. The factor score is not equal to the loading times the variable, right? It's in the way I've calculated them, it's a projection. It's basically related to the loadings, related to information. But if you calculate information for an item, the items with the more information count for more than items with less. So factor analysis is doing a non-equal weighting, but it's doing so by an estimate of how related to the trait each item happens to be. If an item is less related, it receives less weight and therefore gives less of an impact on the score if a person changes their value. How's that? I'm really disappointed the audio I saw wasn't working, but I can't fix that now. On that note, I think I've made it to the end of this. What's that? Oh, yeah, I'd love to do that. Oh, and then finally, I guess the last thing is the predicted item response plots. It's a Lisa thing. No, I made these plots. Come on. Why you know this is not a Lisa is because I made it. It's in R. Sorry. You can tell her that tomorrow. That's true. And you all know what I'm talking about too, right? Because she hates R. And that to me is COL equals 1:3. I can do that, all right? I can type 3 characters. But this is your predicted value of each item response for each item. Remember, the items themselves should have gone. I don't know why I have my dash lines between -1 and 11. That doesn't make sense. It should be 1 and 7 are where those numbers are. And you can see only at the upper ends of the scale are we off, right? So this plot was done. What's that? So this is neither. This is literally taking what a hypothetical factor score would be and coming up with what a predicted item response for it is. So just if you plug in a 0 for F, what's your item score expected to be based on the model, which is what's your intercept, right? And then when F is 1, what's intercept plus 1, the loading plus the loading, right? What this has done, what Lisa likes to do with this plot. Now, Lisa likes this plot. I'm inspired by Lisa to include this plot. She didn't make this, though. That's what I'm saying. But why she likes it is if our items range from 1 to 7, you'll see at the top ends of the scale, we're predicting values that aren't possible in our items. And that is a sort of, she uses this as an index of how appropriate is our factor model for the data that we use. Now, it's I would call it ad hoc, maybe like sort of just like there may be some really good theory behind it. I'm not aware of research done as to whether that's a good indicator or not. I suspect it probably is. I don't think she's done a study for it. Anybody looking for a dissertation topic? But why this shows up here, though, on our slides, is that in next week when you're watching videos of her not ripping on me like I ripped on her. I didn't rip on her today, did I? No, Mom and Dad weren't fighting. Were we? Okay, hope not. When you watch that, next week's categorical version, when we treat the items as categorical, first of all, we wouldn't be able to make this plot because there's no discrete part in between. What we would come up with is the probability a person would select each response. And then we could do a weighted average and come up with something like this, or a weighted average for the average of the item, but nothing that would look like this itself. Right? So there you have it. And we have 3 minutes. Any questions about any of this stuff? Yeah.
So the latent variable actually doesn't necessarily contain what you want. It just contains the information from everything that's in common amongst whatever you are.
Yes.
You're just hoping that's only the thing that you're looking for.
That's a good way of putting it. The latent variable, if you did not know about model fit, the latent variable that you got would be its projection onto the shared correlation among all of your observed variables. That correlation, as we saw in this example, could be truly because of the trait, or at least we think it is, or it could be related to some methodological scale development issue, like negatively worded items impacted this. And without model fit, you wouldn't know which is which, right? So model fit is imperative to determining trying to establish what the validity of the latent variable. But then the other part of it is the model doesn't fit. The remedy to that can build a better scale because you understand the features that are sort of detracting from it as it goes forward. So what I'm saying that for is, you're right, the factor itself is shared correlation, but to the extent it fits, fit is really the determining factor, right? Does that work? How about everybody else? Other questions? Or you, Michael, if you have another question too. Factor analysis is wild, isn't it? It's crazy when you try to measure something that doesn't exist. Ask the physicists, right? What is that? Like to measure something, you end up changing its state, like in quantum particles or something like that. You can't fully. I mean, it's bad. We have this. Although we're not in quantum, this is us trying to map on behavior, which is literally circling a 1 through 7 on this form. But exactly, right? It's that measurement is a really difficult thing to do, and psychological measurement is at such a level of abstraction. It's really hard to do as well too. But, when we walk around with an fMRI machine that's small enough to be on our head, maybe it'll be different. No. All right. At that, let's stop. It's the end of class. Thank you for being here. Thanks for being attentive, and thanks for your conversation. Grateful to all of you for that. I will not be here next week. Once again, don't come here. I mean, technically the room's open. You can watch the video from in here, watch Lisa's videos from in here. And then in 2 weeks, we'll have our exam. I'll probably send a couple of reminder emails. I will have office hours next week if you'd like to chat. And I will have office hours the following week if you have any questions about exam prep or any of that stuff as well too. Okay? All right. Thanks, everyone. Take care.